trust the clock in the back of the room. Okay, so it's time to sort of get serious here about doing something. So this is not a come to lecture class and get a pass. You have to actually do something. So you need to be able to bring up an HTML instance and do something with it. And if you haven't, and you're not going to be able to, then maybe this is the wrong class. So this is, my intent here is to see you do something. So in particular, to get a pass, I want to see you download and run H2O. Connect to, your choice of R, Python. You can use the web interface for a lot of this. Load some data sets, and I'll supply a data set later in the semester for people to do something with. You're going to have to do a workflow that I need to be able to repeat. So you have to hand me a script that I can run and see that I get the same answers you get, right? And then I'll also test your model on a holdout data set. That is, I'll keep 10% of the data aside that I won't show you. I'll hand you 90%, and you can do what you want with it. But if you just take 90% and go build a model, you'll overfit like hell. So you have to figure out, how to do test string split and all that kind of stuff, and do some data munching. And then what I want back from you is basically a simple R or Python script that I'm going to re-execute and confirm that I get what you're claiming your numbers are. And then run it on a holdout set and see that you didn't overfit, more or less. It's the only real purpose there. And if you've gotten that much work done, then that's good enough. It's a pass. So it's not how well that you actually are able to predict on the holdout set, because different people end up with different data sets, and you'll have different ability. Some of the data has a higher signal to noise ratio, and some has a lower, and not everyone's going to get a perfect fit kind of thing. But I want to make sure that you understand what it means to do a split. You did it reasonably. What it means to do some basic data munching. You did it reasonably, kind of things. This is intended to be on big data, and so you're going to need to lay your hands on enough compute power to do something reasonable. And there are a couple ways to get a cluster. I'm working with Amazon EC2 people to get free access for everyone in the class. I'll talk about that in a second, but you can roll your own. 1 or 2 fat desktops or a couple of beefy laptops will do the job. If you're putting yourselves in groups of 2 to 4, if you just combine your laptops and use the multicast out of H2O, you should get a quick cluster. Anything smaller you should be able to do with the 2 gig data set that I handed out last class period. And you should work your way through that exercise. The script I used is online at the ICME website, and the data was handed out last lecture, and I can hand it out again if people need it. But to pass, I'm gonna see if I can't lay my hands on some much larger data set, big enough that you'll have trouble doing it on any given laptop. Although if you get a big fat server, you could do it. The goal here is to make you do a cluster, just so that you get the experience of doing something pretty big. On the other hand, if you just pony up your money, you can get a 120 gig cluster off EC2, and that would do these data sets. But the sort of standard middle of the road servers from EC2 clock in at actually less than $1 an hour. I'm thinking you should be able to do this in a couple hours worth of work, especially if you do like all your testing and setup and configuration games on the free micro-sized server on a tiny data set, and then flip to the big box when you're ready to do a big data set. So AWS Educate's where I'm headed for the free version. I haven't looked at Google or Microsoft. They probably have something similar. I'm working on getting free accounts, but everyone should be able to right now sign up for an Educate account, and you get 35 bucks in funny money. So the free instance, which I'll show you here in a second, is actually free, but it's too small to do something interesting. But you can do all kind of configuration games with it. And if we get it signed up properly, we'll be up to like $100 in funny money later. There's tutorials online, and they were actually pretty easy to use. I stepped my way through the tutorial this morning in about half an hour. So it's not out of control here. Let me go find. There we go. So welcome to middle age and reading glasses. So I went to Amazon. I hit the sign up button. I've already signed up. It lets me, so I'm just going to say go. After a second, I get this horrible eye chart. Somewhere in the upper left-hand corner, it says EC2, Virtual Servers in the Cloud. And I click through, and I get something, all kinds of stuff. There's a launch instance button. Let me back up for a second. I went to the tutorials of Amazon, that was the other link, and I went to the first tutorial, which is launch a virtual machine. And he says, click here to open the EC2 console and click launch instance. So I'm gonna go back to my console, I'm gonna hit the launch instance button. Oh, okay, a bunch of other things show up, like what the hell's that about? So we scroll down to step 2, configure. For this tutorial, I'm just taking all the defaults, which is the Amazon, AMI, straight up. This is a dumbass Linux box on the free tier. See, there's some big letters in green, free. Okay, so you can pay money for bigger machines. If I scroll down, you can get fat machines of 64 or 160 gigabytes, and you'll pay some money per hour for those. Or you can get a cluster of small machines, and you can go to spot instances and whatever. There's a lot of ways to lower the cost, and then, you know, I'm working with the Amazon people. We should have this figured out so it's available for free at some point, or on your funny money kind of stuff. I'm taking the micro. There you go. I don't know what the rest of these things do, so I'm ignoring them. I'm hitting the launch button. Oh, and he says I need a key value pair. Let me come back over here to this thing. Step through launch. He says create a new key pair. Okay, the key pair. This is like a lock and a key gets made. They're going to hold on the lock. You have to hold on the key. The key has to be local on your machine, or you lock yourself out of your own instance. It's like, you know, locking the key in your car, right? And once you have that figured out, you know, you're going to launch. So I have a key value pair here, or a key pair called click cme250 test key. I acknowledge if I don't have the key locally, I screw myself, hit launch. Okay, boom, it happened. Instance is launched. This is my instance name, some horrible I don't know what the hell. I'm going to click through, and it's going to come up, and ignore the click up notifications. Okay, so a bunch of things come out here. This is the instance ID. I'm on US West, Northern California, poking in the upper right corner there. Scrolling around on, here's the scroll bar, way out here, there's a public IP. Where's my public IP? Why isn't it showing up yet? No. Maybe it's still initializing. I don't have it yet. Let me switch back. We'll come back to this in a second. So I made it past the tutorial page, made sure I was on Northern California instead of, you know, East Coast. I'm following the tutorial along. You see my ID number is different from last time. I took the micro one. I have my key value pair. Locally on my disk, I have this, click CME. This is a file I have on my local disk. I got a public IP when I made these slides this morning of this, but I'm certain this guy's going to give me something different here.
Oh, yeah, you have it.
It came up. Okay, good. So it took a minute. I have a public IP, 52, 53, 195, blah, 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 blah. And I'm going to log into the public IP, which I got off the console. And you can't see in this eye chart, but here I did a change directory in ls. Here's my PIM file. Here's an SSH. Well, what's the SSH? It says SSH-I, my key. They have the lock, that's my key. And then the public IP address, I'm pulling off that page there, and I'm just going to be Mr. EC2 user. I have to plug in my PIM file on my local drive and the public IP from the cloud. And I should be able to log in, and let's just play the game real quick. Somewhere in here. Okay, so here is my, well, people read that at all? No, it's probably an eye chart back there. Let's see if we can fix the font here. Hello, text, let's try, let's try 12 point. See what happens here. How about that? Is that better? More or less? Fine, go back into Amazon console. Where the hell's my address? There it is. Back. Can't type. No, I didn't cut and paste. Try again. I did not do that for 52, 53, 185. 53, 185. Okay, so I've just logged into an Amazon instance, live on the spot to an LS. It's a Linux instance, there's not a whole lot here. I need to upload H2O if I'm going to run H2O here, but I can certainly ask Java-version and see. I'm looking at 1.7.099. It's a late rev of Java 1.7 on this tiny box. This is fine. So this is the the workflow I want you to figure out so that you can run and do data science. So the people who came in late, let me say, I'll repeat this again here. Maybe roll backwards. Come on, back. Wow, this looks really slow. Go backwards. Let's try again here. This one. To pass the class, you're going to have to do some data science. So that means you're going to have to do, download, install, and run H2O somehow. You're going to have to connect it to an R or Python. You're going to have to load a data set that I'll supply later, do some basic data munging, build a model. You have to be able to script it. I have to be able to rerun your data science. So I need a script from you that I'm going to plug and chug. And knock on plastic, it does the same thing that you're telling me it's doing. And I get the same numbers that you're going to report. And then I'm going to run it on a holdout set. So I'm going to take a big data set, slice off 10% and hide it, give you 90%. And the goal for that one is that I'll catch you if you're overfitting, right? And then you go to town, do what you're going to do. And you do hyperparameter search, and you do test train split, and you drop the dead columns, and you go do joins with weather or locality or what the hell you do, and you come up with a model that looks interesting. I have to repeat that workflow, and then I'll run your model also on my holdout set. And if you've done those steps sort of reasonably well, that's it, you'll pass. The actual quality of the model is not really important here. It's important that you understand the workflow. And in particular, people have different data sets. Some data sets have a very high signal-to-noise ratio, and some others have a lesser one. Not everyone will get a data set or be able to build a model that fits perfectly, because it simply won't be possible. Yeah?
With this script, would the data size fit on your laptop, or would you have to be on AWS for this assignment?
Let's see here. Why are you not paging over here? Hello? Wow. Interesting. So the goal here is to work on a big enough data set that you need a cluster. And here's some ways to get clusters. So I'm working on EC2 as a way to get people cheap access to a cluster. But you can roll your own if you get a couple desktops together. Or you can certainly practice with getting 3 or 4 beefy laptops. You and your friends in a group or your neighbors and sit down in a place with you got multicast, you can get a cluster going. Anything you do up here or on lesser machines ought to be able to handle that 2 gig data set I handed out. So you should be able to just, without building a cluster, just using your laptop, grab that 2 gig data set I handed out last time, run H2O, and do something with it. And if you're not getting it that far along, then maybe you're not in the right class. Right? Okay, eventually, when we do the pass grade, I'm going to pull out a data set that's much larger. And you'll have trouble running it on your laptop. And you'll have trouble running it on most desktops.
So this assignment is for the end of the quarter, and the lessons up to that we're gonna talk about how to do that, or is it something that?
That's what we talked about all along. Yeah.
No, but is it,
Yes.
are we going to go through the?
I'm not going to step you through.
Not step you through, but go through.
The workflow I talked about the last 2 lectures will be totally sufficient here. Load a data set, build a test model, see that it sucks, figure out why it sucks, go back around, iterate till you get something that's reasonable, and then you're done. And that's good enough. What I want you to be able to do is go into some other company down the road and talk to somebody who's trying to do some data science to solve a business problem and at least know what the buttons are to push. Maybe you don't push them very well, but you at least know what the hell they are, right? So you don't make obvious mistakes. You don't make mistakes that would embarrass me. I took this class from Click, and then I did this, and I'm like, oh. So right, this is how to get you past that level, where the mistakes you make are at least not blatantly obvious. There's going to be subtle mistakes you don't know, and you've learned to find. But let's cut out the bad ones up front. And just know that available to you is the ability to go haul in a big data set. So it's not an instant blocker to forward progress. Oh, this guy's got a terabyte, I'm dead, can't do anything. No, well, you can do something. Right.
Yeah.
All right. Okay, so what I did with my little AMI instance there was I just logged in to cluster of 1, tiny little thing. Up in the top right, it's a Java S version, got that version just reported. What I didn't do is upload using SCP, which is secure copies, this is Linux, right? For the secure copy, you have to put your key on it. I gave it a jar file. That H2.jar I just got from the H2AI website. And then I had to give my username, and then that's the global public key, public IP address for that particular instance, which is different from when I just booted. And that's just my home address on that instance. And if I do that in about 5 minutes using the bad Wi-Fi at Stanford, I will get a jar file uploaded. And then I can do this, java-jar, and it begins to spew out all the normal stuff. And then because I didn't do tunneling, I can't go with the web interface, so I actually did this SSH command instead of the one I showed you before, which includes a tunneling -L option. And then I can go to my local machine and pull a flow using localhost 5555, because that's that 555 there, and up it pops, and I have an instance of one node that's actually in EC2, and I could have made a 4-node cluster too. All right. So that's the general workflow to get you to having a cluster in EC2. I'm trying to work with the Amazon people. Hopefully by next time I'll have out an AMI, and it'll be the same exact steps you're doing here, except when it says launch an instance, you'll launch with an AMI, which will be pre-canned with H2O jar file in there and some toy data sets. And when it comes time for like the actual project, I'll have another AMI that'll have a fat data set in there. Okay. Okay, just repeating, if you're having trouble getting things downloaded and installed, talk to me after class. I want to see what the issues are people are having. If it's you haven't tried yet, then go try first and then talk to me. Okay, so that's what's coming. Are there any questions on that? I'm going to spend the rest of the lecture period talking about how the clustering technology works. So this next piece will not be data science at all. It'll be computer science. How to build and run it. Why a cluster works. How does it work internally? Okay. So we studied it already. I've been talking about this H2O thing. It does a lot of fun stuff. It's one of the fastest ML tools out there for big data. And it has a very strong focus on data scientists and enterprise level work. So there's a lot of interesting bells and whistles in there. And along the way, it does obviously clustered computing. And the rest of this talk is not actually about the math or the machine learning. It's about how to do big distributed cluster computing. So it's like a low-level systems engineering talk with clusters and high-performance computing and memory bandwidth and stuff like that. And actually, I am hiring people if you're interested and this is your forte. But my read of the class last time was there's like 80% of people here are in the physical sciences somewhere, and 10% are comp sci, and 10% are like econ, business, and poli-sci. It's kind of an interesting blend. So the platform basically enables doing almost anything you want on big 2D tables. So any piece of Java code that reads or writes a single row going across, which would be an observation in your data set, like a passenger in the Titanic data set, and or nearby rows. The speed typically is limited by memory bandwidth. You can do enough math per row that you get CPU bound, but usually you're memory bandwidth bound. So you want the data compressed. So it's compressed under the hood, and that runs you faster through the memory bus than uncompressed. The data types are limited to things you can do math on, so numbers and time, strings to a limited extent, to the categorical values we talked about. The width is, it's geared for tall and skinny. So less than 1,000 columns wide, we were looking at data sets with like 50 columns. Those are all really fast. 10,000 columns still works pretty well. 100,000 columns, the loops are parallelized the wrong way. They work, but painfully. But there's no limit on the length, and I have, in fact, tested the trillions of observations. So most simple Java just works using this very clean MapReduce paradigm. And the key there is that each of the different maps are going to read this giant array with basically the same speed as plain Java array loads. It's going to be memory bandwidth bound. You can do writes with compressions a little bit slower, and conflicting writes, if you're into parallel computing at all, you know what a conflicting write means. It's supported, but not recommended. And it won't be necessary for anything you guys are doing. So mostly I'm here to show you this, the quick look at what the data is doing and where and how it works, and how the compute works, so you understand the mechanism behind. So the data is stored as a collection of distributed vectors. You can think of them as an array that happens to be distributed. The length of the array is more than 2 to the 32, right? It can be much larger. You get fast random access with at and set. There is a notion of a missing value. It's a Boolean, so this value is missing, and with the variable size, you can add or remove things along the fly. So it's a single giant vector. Internally, conceptually, you can think of it as a Java primitive. It's a double, but internally it's compressed. You don't know what it looks like internally. The length might be more than 2 billion elements. And you're guaranteed that linear access is memory bandwidth speeds. That's the main design point, is that it's easy to write code that's going to run fast. Now it's big, so it's going to be distributed across your machines in the Java heap. So it's on heap, not off heap. And it's split this way, so that each of these 4 heaps is taking 1/4 of the data spread around that way. And of course you don't have one column, you have a bunch. So Titanic, we had passenger class and passenger name and age and the count of siblings and parent-child relationships and where they got on and off and what they paid for ticket fare and whatever. And so you have some columns going across. So this is very similar to an R data frame or a Pandas, Python, scikit data frame. The collection of these things, the vec array I showed at the top, is just a simple cheap pointer. So you can add and drop columns for free. You reorganize them, rename them. And that's what happens a lot when you're doing exploratory work with the data. You saw I renamed columns, I dropped columns. I didn't reorganize them, but I could have. I might want to group certain kinds of columns together for easier understanding of what the hell's going on. The layout is essentially a struct of arrays versus array of structs. People know what the hell I'm talking about there? It's just like a basic, I turned it 90 degrees. I see some heads nod and some blank stares. It's all okay, fine. And I'm going to guarantee you can randomly access anything you want from any JVM, but if you go in order down the line, it will be fast. Within each vector, it's broken up into these chunks of data, and the chunk is typically 1,000 to 1,000,000 elements, and that's my unit of compression. And I'll change compression strategies every 1,000 or 1,000,000 elements. It's one of the reasons we get such a great compression out. And I guarantee that the decompression happens in just a few machine clock cycles. So the access time is almost always cache miss to go get something. Once you got a cache line in, you have to decompress. Decompress is a shift scale add kind of thing. On an x86, it's got way more CPU clock cycles it can handle. So it's all essentially free, buried in the cost of the cache miss. Within a chunk going across this way, a single CPU will have private access, so it's single-threaded coding style. It looks like it's going to run parallel, but it's going to act like you're writing single-threaded code. And any one core then can go access this row as if it's his own little private playground and read and write however he wants without interference from any other core. And that's the single-threaded model. It's a big enough piece of work that lets me cover the cost to launch another thread, and a small enough piece of work I get good fine-grained data parallelism. On these big data sets we're talking about, you probably have 100,000 chunks on a node. So it's enough to keep the CPUs busy, doing whatever you're doing. And of course, it's not one core, it'll be all cores. So you go say something like, hey, go compute, standard deviation across these columns, whatever it's going to be. All the CPUs are going to grab some chunk of work and work in parallel, through the data set until the job's done, where H2 is handling all the inter-node communication and data management behind your back. So there's a taxonomy here that you'll see. There's a frame, and this is the parallel distributed data frame. It's a collection of vecs. So the frame is a lightweight thing holding on to the column names in the order where the columns are addressed. The vec is the header for a single array, and the array is very large and distributed. And that is spread across multiple nodes. And then a chunk is within one node, it's 1,000 to 1,000,000 elements. And there's a pile of them taken together going this way on different nodes will together make up a vec. And then an element is conceptually a Java double, but under the hood it's something different. It's whatever compression does to it. People have Boolean data, it'll be a bit set. People have sparse data, they'll be run length encoded. You have an enum, the strings are stored somewhere, but the actual value is some small integer mapping to a string. So, you know, it says male, it says female, it says, you know, sleet versus snow versus sunny versus whatever. Those are all the strings. The strings are not stored. They're one-time stored somewhere. You just have a small integer. And then the integer is compressed however you compress integers. Okay. So we'll take a look at the coding style here. So it's a MapReduce paradigm for all the work. And the map is a map, it's a classical map from type A to type B. So the A type is your big data, billions and trillions of rows. The B type will be both a big piece and a small piece. The big piece has to be distributed. By definition, it's too big to fit on your one machine. And the small piece will be whatever you get out of a reduction or a rollup. So I call Pojo here, it's plain old Java object. Some piece of Java structure you've written that you're going to put results into. So reduction then takes two B objects and makes a single B, and that's how you keep collapsing from the trillions down to something that will fit on one node as a simple result. The input and the output type have to be the same type on the reduction there, because it's going to get reduced over and over again in a logarithmic style, you know, hundreds of times. And the basic coding styles, you're going to extend class Mr. Task, MapReduce task there, override MapReduce, and say new and hit the go button. And let's take a look here. So new Mr. Task is a Java object in my code. Suppose the goal here is I want to go compute, find the median. It's a 50% quantile. So a way to do that is do a 1,000-way histogram and figure out where the 50th point lands in that 1,000-way histogram, and then go again on that 1,000-way histogram, slicing 1,000 times again in that one bin that you've picked, and repeat it. So you get a logarithmic reduction at 1,000 times 1,000-fold each pop. 3 iterations will do a trillion rows. Did I get that right? 1,000, million, billion. 3 will do a billion. 4 will do a trillion. There you go, fine. So you know, the Mr. Task object would say, hey, I've got a bin of an array of 1,000 things, I'm going to do counts. And you say do all on data, and you get an object here on one JVM you're going to do something with. And he says, well, I don't have all the data, somebody else has some of it, I'm going to pass it out. He tells his two neighbors in a logarithmic tree fan out, they tell their two neighbors, and so on, until logarithmic in the depth of the cluster, everyone has a task object. And I zoom in, we look at the guts of one JVM. He gets a task object over the network, and he fires it up and says, okay, what do you do? And he says, okay, I need to touch all the data, and I'm only good for one chunk, so I'm going to clone myself and say, you do the other half of the data. And then that's too much, so I'm going to half again. It's a classic divide and conquer, and they do forking, more and more, until they get down to a task that's one per chunk of data. So there may be 100,000 of these, 100,000 chunks of data on this one JVM. And then they start executing the map call on the chunk of data they have. Each individual task is its own single-threaded execution on this wad of data. If it has an output, it happens in parallel to the data here. That's your big data output. If it's a small data output, he gets it put back into his own task object. And you know, talking about the quantiles, that 1,000-way histogram, he's got an array of 1,000 things. He's got an array of 1,000 counts when he comes out down here. I'll show an example of that here in a minute, of what the code looks like. The end of running any pair of maps, we do a reduction, step by step, in reverse, pair by pair. The reductions do not wait to the end like the Hadoop MapReduce model. They happen on the fly as a pair of maps are done. They are done consistently, so every step in the split reverses in exactly the same order, but not in the same place and time. Depends on how the load balancing went after the work. But if you did a pairwise split this way going out, you get exactly those reductions going back. So in the case of doing a histogram, I have a bin of 1,000 counts and a bin of 1,000 counts. I just do essentially a SAXB and add, or DAXB and add the two arrays together element by element. And then you repeat that rolling backwards until on one node you have all the data, the roll up for that one node's entire data set. Then you go back up the cluster. So every node at the edges begins pushing their array of 1,000 element values up the cluster one by one, doing reductions on the nodes as they go, and it works its way back up the log tree, so logarithmic in the depth of the cluster, you get the data back in the original instance that you started with. Is that clear? More or less? So here's some bits of coding style that are going on inside of H2O, and then I can show you like actual stuff, because it gets a lot more complicated. So here's a map that is from type A to type B. The type A is a double, type B is a double. It's not required that they're the same type. It is in this example. It's just using sum of squares. The reduction takes two type A B's and makes one by just adding them. And then I can write this, 5 lines of code, hit the go button, and run across a trillion rows in a second or two. I can have more state in my Java object. So here I have 3 sums. And again, my input state is now a pair, A and X and Y. And my output is the 3 sums. This is the Java object, LR past 1. So this is the information you need to run linear regression past 1. Best fit line to a data set. It's just, that is the entire code for pass 1. There's a pass 2 that looks about the same. There's a pass 3 to compute your R-squared coefficient, and you're done. The implementation lets people do chunking or write at the chunk level, and that leads to a lot of code speed efficiency. So the prior code will work, but this is much faster, and this is how all the algorithms in H2O are actually written. There's a for loop. From 0 to n. What is n? Well, it's the length of one chunk. But it's going to run over the entire array, just chunk by chunk by chunk. The cx.at calls, that's your x and your y doing decompression. That has the same semantics as an array load. But I need to make a function call because they can decompress. And the decompression is different by chunk type. So I don't know what actually happens under the hood there, but it's some sort of version of shift scale add or bit set lookup or run length encoded thing or whatever the hell it is. And then you do the regression map just exactly as I had in the last slide. It gives me code that will go at memory bandwidth speeds on compressed data and do the math. So here's a filter. Counts people who pass the filter. Right? Your age is less than 17, your sex happens to be male, and it's the same code as you saw before, more or less. A few more bells and whistles on this one, but it's the same idea. Here's something I want to ask a question about data. Here's how I can do it. Here's a version where I'm collecting people who pass the filter using an append call. And here I've done the batch thing up front, so it's a for loop. Then there's the filter test you just saw a second ago, but now done at the chunk level. And then I grab people who pass the filter and I threw them in another chunk. And the way to fire it off is I say, make me a new vector that happens to be one I'm going to grow on the fly, make a filter object, do all, and then I got back the list of people who passed the filter. Now that filter might be a 99% pass filter. So if I hand you 1 billion people and I did a 99% pass filter, I got a result that's like 1 billion in size. And so it has to be distributed as well. So this is a distributed result. It's not a small Java result, it's a big result. Here's a histogram example. I've got an array. I'm counting the number of cars people own by the age they are. And so I'm just going to do a lookup on your car count and your current age and do a plus plus. For people in the comp sci community, the plus plus is known to not be thread safe. It's a load, add, store as 3 separate operations. If you run it in parallel, you'll have collisions, you'll have conflicting writes, and you'll lose counts. But this code's running single-threaded. So it's running single-threaded because the map runs in one thread, and he makes a new car ages array in the map call. And that gets that one core that's doing the work on the one chunk a private array. It's this private piece of data no one else has, and so he gets to do what he wants with it without worrying about concurrency or consistency. So he writes single-threaded code, it works. However, since I did a new array for histogram there, per chunk, and I have 100,000 chunks, I have to roll those arrays up. And that's the reduction step. And here I have array utilities to do an array add. There's an element add of the 2 arrays. Here's a distributed hash table. This one has I'm going to do unique counts with it. And this one, I am putting the constructor for the hash set putting the hash set constructor in the Mr. Task constructor, which means at the time I say new uniques, I made an instance of a hash table. So when I say do all, that one hash table gets passed from the cluster and everyone's sharing it. So that add call has to be thread safe. Otherwise, and that's why it's a non-blocking hash set instead of the plain hash set, because everyone's sharing the same hash set. Now it is cloned per node, so they're only sharing on one node. They're not sharing, of course, across physical distributed systems. They can't. So you still have to have a reduction. And a reduction put all here takes the two different hash sets from the different places in the node and rolls them up together. And so, whatever 7 lines of code here, I can go ask for unique counts across a cluster. And it's sort of a unusual operation. And also, this will still run as fast as a couple seconds a terabyte kind of thing. Fraction of a second per gigabyte. So the basic idea here is the code's going to run distributed, so you can't do things that do I/O or machine resource allocation. You can't make new threads, new locks. Locks are local on the node; they're not global. You can't call system exit or you just blew the brains out of one of your cluster members. There's no global variables because they become node local. But if you have global state you want to do something with, if it's small global state and it's readable, you put it in the constructor and it's just going to get cloned around the cluster and everyone's going to shallow copy and share it. So it's the ideal sharing pattern. If you have global writable state, you have to use a reduction. You got a trillion things you're going to add up, you must use a reduction. If you have big state, whether it's readable or writable, it has to go in and out of those distributed vectors. Because by definition, it just doesn't fit on one node. You just can't pull that answer back. So in particular, if you're doing this data science project and you have a 40 gig data set in an EC2 cluster, and you're in Python and you say, as pandas data frame, then that 40 gig data set will download over EC2 to your laptop until your laptop runs out of memory and crashes. So you can't pull the data locally, right? And then the coding styles, you're going to run one big step to completion and then another and another and another until you get whatever interesting project done you want to do. So the strengths of the code is that it runs distributed in parallel without further effort. You write for I equals 0 to n, do something with a 2D array, and it just works. And I'll show an example here, but I've had lots and lots of examples of it. And it runs on millions and billions of rows and thousands of cores, and you're writing in a single-threaded coding style. There's no knobs needed for GC or CPUs or networks. There's no hot locks. There's no hot blocks. There's a lot of the issues that people have sweated with over a long period of time don't actually happen here anymore. It just works straight out if you can write code in this style. So here is an example of k-means, right? It's an eye chart. Like, what the hell is going on here? Okay, I'll step through at a high level real quick, but you don't have to know anything here or even be able to read it. Somewhere at the top, I got a bunch of input fields. I got some output fields. So this is the Lloyd's pass in k-means. It's going to do the sums of squares of distances to the nearest cluster member. It's a standard thing. There is a constructor which just is copying fields around. There's a map call, which is at the top. There's a bunch of news. It makes a bunch of private arrays. And it has a for loop for I equals row equals 0 to length of chunk, do something in a for loop, which looks like pull some data out, computer closest cluster to it, sum you into the closest cluster, do some quick math for, this is where you get added into the cluster in choice. It's k-modes as well as k-means, so it's doing stuff with categoricals. There's some scaling issues that we have to take care of once we've got a new cluster center. There's a reduction of taking pairs of computed partial cluster results and doing reductions on them. And the sort of real takeaway is that I have like hundreds of Java classes written this way, tens of thousands of lines of code, and it's been written by mathematicians who are running math. Now we're making it run fast. So sort of the big takeaway is this is a coding style that actually works. You don't have to be a systems engineer, you don't have to be a cluster guru to make it go. In fact, I have a mathematician come in who's never written a line of Java code in his life and write Cox proportional hazards in a month. And it just, out of the box, it ran fast. And once you got past basic debugging and it did Cox proportional hazards on small data, it did it on big data too. Okay, I'm going to touch the block architecture because you're going to deal with a piece of it, and then we don't need to play with the key value store stuff. That's going to be overkill here. So here's a high-level block over diagram. It's it's a standard bubbles and arrows picture, like what the hell the parts do. So the one in the lower right corner is we call an H2O node internally. It's a proxy for the local resources, local CPU, local memory, local disk. So buried in here are things like how many CPUs you have, that's how many threads I can launch, that's how many cores I can run in parallel. How much memory do I have? When do I run out of memory? How do I track that? When do I spill the disk? Fork join is the distributed data parallel working operation where you keep forking off new pieces of work until the job gets done. There's a reliable RPC mechanism because I do both TCP and UDP, and under high load, H2O can look like a distributed denial of service attack. And under a modern Linux kernel, he will shut down TCP sockets because he thinks you're doing a DDoS attack to itself. And so I have to like back off and relaunch the TCP connection and go again. So it was an unusual, difficult thing to go debug why that happened. So built over that is a reliable remote procedure call, and then there's a key value store, which I'm only going to touch lightly on. There's actually a really high speed, high value, or high quality key value store buried under there that no one in this classroom actually needs to play with, but it's there if you want to mess with it. There's a serializer, and yet another Java serializer, really? Well, it turns out that I made different assumptions than many people. In particular, I'm only doing cycle-free data because this is math I'm doing and not computer science. I don't have a lot of cycles in the math. The schema is unknown in advance, so I have to pass that around the first time somebody touches a new Java object. And then I do codegen on the fly, and a lot of compression, and the combination puts me at memory bandwidth speeds to read from a Java object and write into a network buffer, and so I can overrun network buffers, and networks are fast these days. So it's somewhat of it's a much faster serializer than anything out there by a fair amount, including all the Cairo and Protobuf and all those kind of things. So back to the high-level picture, there's a distributed key value store, DKV. It's a Java memory model with exact consistency semantics, and if you ever play around with other people's key values, they'll talk about what kind of laziness they do. We only do exact, and we do it fast. It's fully caching under all situations. Standard cache hitting get is 150 nanoseconds. Streaming puts will be bottlenecked by the network. It's how fast you can jam writes to another node in the cluster. Supports transactions. The big data is all stored in the key value store. So say I have a chunk of data, there's a key to it. And the key is programmatically related to the vector. And so given a row number, I can go compute the chunk it's in, and that will come up with a key, which is which node in the cluster has it in one step. So I can get from a row number to a chunk of data without asking anyone else. I can go straight to the node who has it and do something with it. I just did a big walkthrough on the MapReduce side of things. This is distributed fork join, which is the whole, spray the work out across the cluster, leave the data in place, do the work in place, and then roll the results back up. MapReduce being the workhorse here, doing all the heavy lifting. And then the last box is the one people will run into. This is the external interface. So the main external interface to H2O is this REST JSON web server. It's built in. There's a REST server. You can code to it directly using curl. And it's useful if you're trying to figure out an independent workflow without using any other tool. Like if you're not comfortable with Python and R, but you've been using Flow and you want to make a scriptable workflow out of it, you can start looking to see what Flow is doing. You'll go ask your browser what actual commands are getting slopped back and forth. And you can write some curl scripts to go do the same things. Mixed in with there is the one of the URL calls you can make is called rapid. So it's like HTTP or localhost 54321 whatever slash 3 slash rapids slash, and now you put a Lisp string, and the Lisp string will get executed on the cluster as sort of an arbitrary expression evaluation. And we use that to do all the sort of big data math munging you saw I was doing in Python last go around, where I said, hey, take this column and divide it by seconds in a day and take a floor. Okay, that was a Lisp expression compiled to and executed on the cluster that way. First class functions are supported, so you can write a lambda that gets passed over the big data. Again, probably nothing anyone needs to do in this class, but it's out there if you want it. The results come back in JSON. So you need to have a JSON parser if you're going to work at that level. But sometimes it's useful if you're trying to figure out how the hell the box is working to poke at it with curl and look at the JSON responses coming back. Okay, that's what I wanted to cover today.
The lambda expression thing
Yeah.
that you talked about?
Yeah.
Is it like lapply, sapply going over like can you give it like a specific example?
It's you can apply a lambda. Yes, you can supply a lambda function to an apply call in the rapid syntax,
Right.
and the apply call will go either by row or by column and apply the lambda function.
So that's what you meant with that bullet
Yeah,
point.
yeah,
basically.
yeah, yeah, yeah.
Okay.
So if you're doing sort of more arbitrary random crunching stuff,
Right.
the what's required for this class is you run the algorithms themselves,
Right.
which are using the Java version of things, and they're not using the Rapids side. The Rapids is for data munging. So if you need to do data munging, the calls right in Python said add a column and drop a column. That was all. That actually came out in Rapids calls too.
Okay. Second question. This might sound a bit dumb, but let's say I have 4 fat laptops.
Yeah.
Right?
Yeah.
And I get 40 gigs of data.
Right.
And I want to view it at the like real time. Like,
Right,
Like,
yeah.
Like
Right.
we look at it in a spreadsheet.
Right.
It seems like let's just say I had 16 gigs
Right.
on 2.
Yeah.
Or,
Well, you
okay,
got
let's just
four.
4. Let's
You got
just do
48
4.
gigs total.
Right.
Right. Yeah. Right.
I would be able to view it, but let's just say,
Yeah.
no, let's just say my data was bigger, so I can never like view it.
Right. So what you're wrestling around with is how do you inspect and view and
Right, like before data
Yeah.
wrangling, even if I wanted to do
Yeah.
some.
Right. So the H2O supplies very basic setup there in the flow interface. I showed last time. If people are curious, I'll just kick it up again. You can look at the column roll-up data and summaries on all the columns from flow. And the H2O itself is peer-to-peer, so it doesn't matter what node in the laptop does it, and everyone can do it at the same
Okay.
time. So if
Okay.
you and your buddies sit up and make a cluster,
Right.
everyone can poke at it via flow all at the same time
Okay.
and be paging around looking at different things at different times. And hand in hand with that, if you start doing data munging, it'll happen in real time for everybody, but whether or not flow refreshes is when you ask for a refresh. So it'll hold on to the view you had, and if somebody took a column and dropped it, you won't notice it until you refresh that view.
Okay.
And similarly, if you kick off a giant, deep learning neural net computation that takes 5 minutes and slams laptops, all those GUIs will become fairly unresponsive
Okay.
until the job's done.
Makes sense.
Yeah.
So I'm a bit confused. When do the MR tasks sort of figure out how the data is distributed, or how do they know how to like access the data?
Yeah, okay.
Is it like in the do all function, or are we
Yeah.
assuming that the vectors are like distributed objects and sort of know? how to
So,
access the data?
okay, yeah, let's do it that way then. Here, take this picture here. So, the vectors are distributed, but what happens here, what I call a vec is is a Java object, is actually a little tiny metadata piece, right? It's a couple hundred bytes best. And he has a key with him, he's in the key value star. And the key has a particular layout. All chunks have that same exact layout except 4 bytes into the key, or replace the 0, 1, 2, 3, ad infinitum. So he knows how to generate keys for the other chunks. There's a hash function which says where the chunk lands in the cluster. So it's pseudo-randomly hashed. For chunks and data in general, the hash function is very carefully selected to force good round-robin load balancing of the data. So given the key that he generates for a particular chunk, he can hash it and say what node it is. And that's part of the communication pattern that goes on with the Mr. Task object.
And is that in the do all function?
Oh yeah. So buried in the do all, he says, what range of chunks am I dealing with? Are any of them non-local? If they're non-local, then fork off to my left and my right with the data range I'm dealing with, and only look at the local chunks.
Okay.
And then local, and he does it by asking the question of, push the hash function through the key lookup mechanism to find out what node you're on. Sorry, push the key through the hash function to find out what node you're on. I said it right. So the point here is just to show you how it works at a high level. The details are all buried in there, and I can step you through exactly where the hash function is. There's some stupid hash function that does a is home question by hashing and doing the math.
Is there like a white paper that is written that actually explains this in detail? Because like some of the terms that I just didn't even understand, I don't know of them.
So ask, because if you don't understand them, other people don't either.
Okay.
So like what turns out, as for white papers, you go to the H2O website, there are some docs.
That goes in depth like this.
Most of the documentation is not here, it's on data science. As far as I know, this and a couple other talks I've done in the last several years have the majority of the internal architectural state.
Okay.
So I do this talk a number of times. You can go find me, you know, my smiling face doing the
Sure.
same talk on video somewhere and
Right.
replay it that way. But I don't have a white paper for you to read.
Right.
And then you say you didn't understand some of the terms. So like what?
You know, when you were talking about, if you go back, like even in this, like FJ load balancers.
Fork join. What is, okay, and what is load balance? And what is fork join?
Yes.
Okay, no, that's the point. That's all good. So fork join is a technology that's been around the block a long time, but it's sort of been buried into the deep systems engineering side of things in high performance computing.
Okay.
So HPC and supercomputer kind of land. Doug Lee did a really nice high quality job of porting it to Java. So I'm using Doug Lee's fork join. It's now officially in Java 1.8. I have a pre 1.6 version I'm running right now. And at some point when I declare the source code running the 1.8, we'll pick up the 1.8 version. But it's a,
So
it's
fork join basically just distributes your data into these different.
okay, so fork join is a technology which says, given a task, make decide to fork or not. So Doug doesn't do it distributed. Let's go find the forking piece here. So fork join is this guy. He's the one that says this task object does a bit of math. Says how much data am I working at? I'm working with all the data local on this node. Okay, how much is that? Well, it's more than one chunk. So he says, okay, divide in half by forking and making two halves, each which are going to do either half. So he clones himself as a Java object. Now, as a Java object, he's a little tiny thing. He's like 64 bytes. He's like really tiny. He's got a lower bound and upper bound on the chunk number, and a virtual table pointer to the code he's going to run, and basically that's it. So he says fork as a clone, and then he scribbles, change your middle point, your low bound to be the mid, change your high bound to be the mid, and now these two ones are each referring to half the data.
Okay.
And then is that one chunk or more than one? It's more than one, fork again, and fork again, and fork again. So the forking cost is on the order of, less than a microsecond. So it's like really cheap to fork. Once you get down to one chunk, you then call map, and the map call runs for milliseconds, 1,000 times longer, maybe tens of milliseconds, right? It's much longer. So the map call then runs over the data and does some work. When you're done with that map call, at the last thing he does, he says, I'm done. He asks the question, he flags he's done and asks the question, is the other half of the fork done too?
Okay.
If it is, do a reduction right now.
Okay.
And if it's not, just you're done.
So,
And go back to the work queue and grab another task and go again. And then the elegant engineering in fork join is how to keep those work queues cheaply available for people to grab, do work stealing if you have imbalances in the data set and the amount of work being done, so that one core can go grab work from another core, but still have launch times that are in the order of microseconds. So the actual overhead of launching a fork join task and stopping it are in the order of low microseconds. It's really fast. And then the amount of work I do per chunk is actually much larger because of the size of the chunks. So now what's load balancing? Is it that comfortable with what's going on there? People know what I mean by load
You
balancing?
balance the amount of work that you send in and how.
So I have an 8-core box.
Right.
It's got 8 CPUs.
Okay.
I've got 1,000 pieces of work to do.
Right.
If they're all uniform, it all lands about the same. They all grab one after another
Right.
for the 1,000 pieces till they get to the end, and then the last few things people go idle one by one by one.
Right.
But suppose it's highly imbalanced, and I have one chunk of work that's going to take half the time, and the rest is pretty cheap.
I see. Okay.
Right.
There's a bottleneck. And
There's a bottleneck somewhere in there.
Right. Okay.
Okay. So load balance is somebody got busy and is supposed to handle a lot of work and doesn't ever get to it because he's doing too much other things.
I see.
And you can go take some work from him.
Okay.
And that's work stealing. You
Okay.
steal some of his work and you go do it. So the load balance is only possible because I've broken my work up into these 100,000 chunks.
Right.
Each guy starts out by saying, I'm going to take half the work,
Right.
right? But that's too much.
But then it's not uniformly
And it's not uniformly distributed.
It'll have
So
a-
halfway through the middle, some other core says, wait a minute, I'm bored, I'm idle.
Right.
You said you're going to take half, but you're only through like a quarter of it. You've got 3/4 left. I'm going to go grab a chunk of that and go. And that's load balancing. And that keeps all the cores like running. You watch a perf bar go, all the green lights light up and
What's a
everyone's really
perf
busy.
bar?
And they'll die down. Performance bar. What are the
Okay.
CPUs doing?
Okay.
Usually it's green for they're busy, red for caught in the kernel, sometimes white for I/O, blue for idle. It's a performance thing when we're trying to figure out why the cluster is going fast or slow. And the usual story is somebody's got a bottleneck doing single-threaded work, and it's taking them forever to get done because they're doing single threaded on a trillion, and it's just, you know, it's not gonna work. And then you have to go back in, oops, I forgot to parallelize this piece, and go make it parallel and go again. All right, is there any other questions on like just numerology here, names, jargon?
How about reduce? What do you mean by when you're reducing to come back in?
Okay. So having run a map in parallel across a lot of things here, I've got results in different objects. The results, you know, I talked through, didn't show much code on, was I did histogram. So classic histogram is I break up my data from min to max in 1,000 buckets, and I add a point in each bucket, you know, count of one in each bucket that depending on where you landed. So I take the ages of students on Stanford campus. They range from what, you know, 18 to 30. I don't know what the hell, right? I have this, and you know, maybe it's 14. I don't know. And you put counts in these buckets, right? So at the end of doing a whole pass through all of the Stanford campus, I have a histogram. But suppose I want to do this in parallel, and so I send everyone in this classroom out to go count a different set of people in Stanford, and everyone gets their own count of a subset. Now to make this work as an actual histogram of everybody, we have to run these counts together. And that's what the reduction is going to do here. It's going to say, oh, you have some data, and you have some data, and I have some data, and some other person. You and I get together, and we add our counts up. And then one of us walks away with the bucket of counts, and the other person's free to go. Again, I got my bucket of counts, and you're free to go. But this guy's done the same thing, so he and I have to fold together. And again, he's free to go, and I hold on to the buckets because I'm a professor, so I'm going to hold on to all of them. And then so on and so forth. Now, if I touch everyone one at a time in this class, I had to touch 40 people. But instead, I make you pair up. Right, and that's the logarithmic roll-up. So you and your neighbor do it, and you and your neighbor do it, and you and your neighbor do it, and so on and so forth. And then everyone does one roll-up, and then half the people are free to go, and half the people have to do one more roll-up. Right? And that's this one.
So this reduces your computation stuff like exponentially, basically?
Yes. It gives me a logarithmic runtime instead of a linear runtime. So it's not count of people in the class, it's log count of people in the class. So it's not count of chunks in the cluster, it's log count of chunks. How many chunks are there? Well, the chunk is just divided by 1,000,000 of the amount of data. If I've got 1 trillion rows and I'm dividing by 1,000,000, I got 1 billion chunks. So I don't want to do 1 billion one at a time, right? There's too many. But log 1 billion is like 10, 20. So, it's cheap. That's all I have.
Cool.
The actual, go forward plan here is you guys do something with H2O, get it up and running, do some loading of data, exploration, data science, because to pass the class, you're going to have to do it for real, and you don't want to be doing it cold turkey at the end of the semester. Does H2O run away? Sorry? It runs in Java. It runs in Java.